In the last video, we showed what an aperture is and why the aperture of radar satellites would theoretically need to be kilometers long to achieve the spatial resolution of, for example, 5 meters at Sentinel-2. If you're completely lost right now, then take another look at the video. Radar satellites do not exist. And here is the proof. There, we determined that a high resolution in radar satellites would essentially fail due to physical laws. In this video, we explain why it still works and how physics can help to outsmart physics. First of all, radar sensors look obliquely at the Earth's surface. The pulse emitted by the satellite's aperture hits the Earth as a large oval area and is reflected back. This entire field of view is actually a measurement. All details within this area would actually be lost. To avoid this and ultimately obtain a high-resolution radar image, two problems need to be solved. Firstly, more precise information must be measured at a right angle to the flight direction of the satellites. This direction is called range. The second problem is to generate a higher information density in the flight direction of the satellites, known as the azimuth direction. Let's start with the range direction. The satellite sends out a closed pulse. Since it records, laterally, the distance of objects that scatter a signal back can be determined. Because the further away they were scattered from the satellite, the longer they are in transit. These differences in travel time can be measured because electromagnetic waves consist of periodically repeating waves, crests, and troughs. Each point on the wave can be described by its phase or phase angle, and the sensor can precisely determine at which phase angle it sent out a pulse and at which phase angle it receives it again. Physically, it is said that it can determine how coherent the sent and received signals are with each other. The later the pulse arrives, the more the incoming phase is shifted relative to the outgoing phase, meaning the more incoherent both signals are with each other, and the further away the point is from the sensor, from which the signal was backscattered. Since the wavelengths, meaning the distances between points of the same phase from radar satellites, are in the millimeter or centimeter range, the position of objects in the range direction from the satellite can be measured very precisely. So now we have more precise information about where objects are located relative to the satellite in the range direction, but we still cannot determine their position in the flight or azimuth direction. As the satellite moves its field of view across the Earth, an object remains in this field of view for some time and is illuminated many times by the satellite's pulses. If one could track it over the entire time, much more information about the object's position would be available. This would also allow for an increase in resolution in the azimuth direction. A physical phenomenon also comes to aid in this process. The Doppler effect describes the change in wavelength when the source or receiver of a wave is in motion. For sound waves, it causes the pitch of a siren to increase as an emergency vehicle approaches, and to decrease when it moves away again. This is because sound waves are compressed as the vehicle moves towards a person and stretched as the vehicle moves away. This shift in wavelength can also be measured in objects moving through the sensor's field of view. The wavelengths are shortened when the sensor moves towards the object and lengthen as the object moves away from the sensor. As objects move through the satellite's field of view, the wavelength of the signal reflected by them with each radar pulse changes slightly. This allows the signals of the objects to be tracked over the entire range of the recording area. And with each radar pulse, their position can be determined more accurately. The final radar image is not the result of a single radar measurement, but rather the combination or synthesis of many individual measurements. In this way, not only is the real aperture of the satellite with its very limited resolution utilized, but also a synthetic aperture enabled by the Doppler effect. Hence the name SAR, Synthetic Aperture Radar. Let's summarize again. Because radar satellites operate with long-wavelength radiation, they are actually unable to produce high-resolution images due to physical limitations. However, the properties of electromagnetic waves also help to circumvent these limitations. Thus, measuring the time differences of radar pulses, also known as coherence measurement, helps to improve the resolution in the range direction, that is, perpendicular to the satellite. The measurement of wavelength changes through the Doppler effect, which enables the creation of a synthetic aperture, leads to a significant increase in resolution in the flight or azimuth direction. Thus, the laws of physics cannot be circumvented. However, when properly understood and applied, physics can sometimes outsmart physics itself.